Hello everyone, I am Dr. Manasvi Dixit, Associate Professor of Physics from SKIT College, Engineering, Jaipur. Today I am going to explain the basic concepts of laser with the help of this presentation. This is the contents of today's lecture. First we will discuss a short introduction of laser, characteristics of laser, basic principle of laser action, along with some few more topics which are given here. Laser is an acronym wherein L stands for light, A for amplification, S for stimulated, E for emission, R for radiation. That is light amplification by stimulated emission of radiation. This is how we define a laser, that laser is a device which amplifies the infrared, visible and ultraviolet electromagnetic radiation on the basis of stimulated emission process. The phenomena of laser was firstly introduced by Townes and Scala scientists in 1958, which is based on wave-particle duality of light, which was given by Einstein in 1917. Here, this figure shows the laser of different wavelength or colors, and all are lies in visible region. Now we come to the characteristics of laser. As we know, the laser is a special type of light. It has some unique properties that differentiate laser from any other ordinary light. These are few. First is, it is highly monochromatic, that is, it emits only a single wavelength or colors which has very small bandwidth. Second is, it is highly coherent, that is, all the emitted photons of laser are in same phase and travels in a same direction. That's why it is also highly directional, and the angular spread of laser is around 1 mm per meter. Due to this highly coherent property, the intensity of laser is very high and it can focus very small area, approx 10 raised to power minus 6 centimeter square. Because of these unique properties, laser light is highly powerful and is capable of propagating over long distances. Now, this slide shows the difference between ordinary light and laser light. As we can see, the ordinary light spreads in all directions and has many wavelengths or color, whereas the laser is more directional, having single wavelength. In laser, all the emitted wave trains are in phase, but in ordinary light, there is no specific alignment of emitted wave trains. One thing the student should know, that having these unique properties, laser cannot be perfectly coherent, perfectly monochromatic and perfectly directional. However, it is far more coherent than light from any other source. Now we will discuss the basic principle of laser. The basic principle of laser action is based on the quantum theory of light, that is how a radiation interacts with a material. This interaction can be explained on the basis of electron transition in energy levels through which a light is to be obtained. According to Einstein, when a radiation incident on a material, three types of process occurs simultaneously. First is stimulated absorption, second is spontaneous emission, and third one is stimulated emission. This stimulated emission is the basic principle of laser action. So in next few slides, we will discuss these three processes of interaction one by one. First process is stimulated absorption or induced absorption. For this, here we consider only two energy levels of electrons of atoms. First is lower energy level of electron, that is ground state of electron having energy E1, and second one is higher energy level of electron, that is excited state having energy E2. Now, when a photon of or radiation of energy h nu incident on an atom, the ground state electron absorbs this energy and jumps to the higher excited state. Here we can see this atom absorbs h nu energy and jumps to the excited state. Since this process is induced by the incident photon, therefore it is called stimulated or induced absorption. The absorption of radiation occurs only if the energy of incident photon exactly matches the energy difference of two energy levels, that is E2 minus E1. Now the second process is spontaneous emission. As we know, the electron in the excited state can stay only for a short period of time, which is known as the lifetime of excited state electron. And this lifetime is approx 10 raised to power minus 9 to 10 raised to power minus 8 second for excited state. Thus, after this short lifetime of excited electron, they return to the lower energy state or ground state by releasing energy in the form of photon. Since in this process the electron move naturally or spontaneously from higher state to lower state, therefore this process is called spontaneous emission. The spontaneous emission process is independent from the presence of any photon in system. Any of the electron of higher energy state can jump to the lower state and produces a spontaneous photon, which is not in phase and not travels in same direction as incident photon in the system. So the photons emitted in spontaneous emission process give a ordinary incoherent light. Now the third process is stimulated emission process. Einstein proposed that when a photon of proper frequency incident on a system, it is not essential that it may always be absorbed by the atoms of lower energy level. It can also be interact with the electrons of atom present in higher energy level and induce that electron of atom to transit the lower state and emits a new photon of energy h nu, which is equivalent to E2 minus E1. Such a process is called stimulated or induced emission process. The photon produced by stimulated emission process is in same phase, travels in a same direction as incident photon. Here in this figure we can see there are two photons produced of same energy and travels in a same direction. Therefore, by stimulated emission process, two photons are produced which are highly coherent with each other. Hence, we get an enhanced beam of coherent light. This is the basic principle of laser action. Now, in this slide, we will discuss the relation between Einstein coefficients which are given by Einstein for absorption and emission process. For this, let us consider N1 and N2 are the population densities present in the ground state and excited state energy level of energy E1 and E2 respectively. Also consider U nu is the energy density incident on a system. Here, population density is defined as the number of atoms per unit volume present in a given energy level. Now, for stimulated absorption process, we know that it occurs in the presence of incident radiation. Therefore, the absorption rate, or we can say the number of atoms going from lower state to higher state by absorbing photon, is equal to B12 N1 U nu, where B12 is the Einstein coefficient for stimulated absorption process. As we know, the spontaneous emission process is independent from incident radiation. So, the spontaneous emission rate, that is the number of atoms going from higher to lower state by emitted a spontaneous photon, is equal to A21 N2, where A21 is the Einstein coefficient for spontaneous emission. Similarly, the stimulated emission rate, that is the number of atoms going from higher to lower state by emitting a stimulate photon, is equal to B21 N2 U nu, where B21 is the Einstein coefficient for stimulated emission process. Now, our aim to find out the relation between these Einstein coefficients B12, A21 and B21. As we know, At thermal equilibrium, the absorption rate must be equal to the emission rate. Therefore, we can write N1B12 U nu is equal to N2 A21 plus N2 B21 U nu. Equation 1. Here, the first term of right hand side represent spontaneous emission rate and second term represent stimulated emission rate, whereas left hand side is for absorption rate. Now, in next slide, after rearranging equation 1, we get energy density U nu, which is given by equation 2 in terms of N1 and N2. Now, according to Boltzmann distribution law, the population density N1 and N2 are given as, where N1 is equal to N0 exponential minus E1 upon KT and N2 is equal to N0 exponential minus E2 upon KT, where N0 is the population density at absolute zero temperature, K is the Boltzmann constant and T is the temperature. So, with the help of this, we get the ratio of N1 and N2, that is equation 3, which is equal to the exponential h nu upon kT, where h nu is equal to the energy difference of two level E2 minus E1. Now, putting equation 3 in equation 2, we get energy density U nu as equation 4. This equation 4 has a very good agreement with Planck's energy distribution radiation law. According to Planck's distribution law, the energy density U nu is equal to 8 pi h nu cube upon c cube into 1 upon exponential h nu upon kt minus 1, equation 5. Now, on comparing equation 4 and 5, we get B12 is equal to B21, that is equation 6, and A21 upon B21 is equal to 8 pi h nu cube upon c cube, that is equation 7. Both equation 6 and 7 are the equations for Einstein relation. From equation 6, it is observed that probability of spontaneous emission and probability of stimulated emission are equal at thermal equilibrium. And from equation 7, it is observed that the ratio of spontaneous emission to stimulated emission is proportional to nu cube, which implies the probability of spontaneous emission is larger than stimulated emission probability at thermal equilibrium. But when a radiation is incident on a system, then this thermal equilibrium is disturbed. Now, in this slide, we discuss the threshold condition for laser action. Generally, spontaneous emission is more predominant in the optical region. To increase the number of coherent photons, stimulated emission should dominate over spontaneous emission. So, for laser action, two conditions are required. First is the emission rate must be larger than the absorption rate, and second, that is the probability of stimulated emission must be greater than the probability of spontaneous emission, that is A21 is less than B21 U nu. These two conditions can be achieved by increasing the energy density of incident radiation, that is U nu, and by decreasing the ratio of A21 upon B21. To increase the energy density U nu, the emitted radiation is made to reflect again and again between two parallel mirrors in a cavity containing active medium. And to minimize the value of A21 upon B21, the metastable states of larger lifetime are chosen for stimulated emission, because from metastable states the transition of electrons from spontaneous emission is negligible, as A21 is equal to 1 upon tau c, where tau c is the lifetime of energy state. For metastable state, the value of tau c is approximate 10 raised to power minus 3 second, which is very large as compared to lifetime of other excited state, that is approximately 10 raised to power minus 9 second. By achieving these two required conditions, we get the threshold conditions for laser action, that is population inversion condition, or N2 is greater than N1. That means for laser action, the number of atoms in higher state must be larger than the number of atoms in lower state. This population inversion condition can be achieved by pumping method. So, to produce a laser light, there are three basic components: active medium, pumping source, and optical resonator cavity. The active medium is the basic material in which the population inversion condition is achieved. The active medium may be solid, liquid, or gas. This active medium decides the wavelength of laser light. The pumping source. It is the energy source which is used to pump the atoms to higher state. The pumping source can be electrical, optical, or chemical depending on active medium. The optical resonator cavity consists two parallel mirrors facing to each other, in which one is fully reflecting mirror and the other one is partially reflecting mirror. The active medium is enclosed by this cavity and it is attached by a pumping source as shown in figure. Now this slide shows the lasing action diagram in which three energy levels are mentioned: ground state, metastable state, and the excited state level. When energy is applied to a medium, the electrons of ground state goes to the excited state, which is unstable state, and within or before 10 raised to power minus 8 second, which is the lifetime of excited state, electron transit to metastable state by emitting a spontaneous photon. Therefore, a population inversion condition is achieved when the majority of atoms have reached on metastable state. Now, a lasing action occurs when an electron spontaneously returns to its ground state and produces a photon. This photon interacts with the electron of metastable state and induces them for the transition to ground state. By this, a stimulated photon is produced which further moves parallel to the laser axis in optical resonator cavity between parallel mirrors and induce other stimulated transition. By this way, a coherent light beam is amplified and we get a highly coherent laser beam. This laser radiation will continue as long as energy applied to the lasing medium. This slide shows the procedure of lasing action which we have discussed in lasing action diagram just before. So with these notes, I am ending my lecture. Thank you for watching.